previous lecture, we learned about free particles and we said that with periodic boundary conditions and box normalization, we have the wave function psi, and I will just label them with k, because k itself gives the energy also, as equal to 1 over square root of L cubed e raised to I k dot r, where k vector is k 1 in the x direction plus k 2 in the y direction plus k 3 in the z direction. R is x plus y plus z, and the density of k points is v over 8 pi cubed, which is same as L cubed over 8 pi cubed. That is the density of k points in k space. This is per unit of k space volume. And if we take these particles to be electrons, then there will be 2 particles or 2 electrons per k point. Each state can maximum accommodate 2 electrons, and therefore, the k space is going to be filled up to some very large value of k, and this is what we are going to determine in this lecture. So, this, as I said earlier, so free electrons provide a reasonably good first approximation for metals. And let me argue that why. So, metals are going to have these ions which are positively charged. Let me make a few, and these electrons which are delocalized and moving all around. Since they are mobile, what they do is they screen out the charge of the ions. They kind of move around these charges, the positive background charges, and therefore, the potential in which they move in a self consistent manner is very much constant. So, potential could be something like this. So, what we can say is that the background potential is nearly a constant for the metals, and therefore, psi k equals 1 over square root of L cubed e raised to I k dot r give a good approximation to electronic wave function for each electron. And in this process, we have also done one more thing, and I must point that out, that we have neglected the electron interaction. And it turns out that even this is a reasonably good first approximation. So, we are going to focus strictly on each electron having its individual wave function e raised to I k dot r, neglecting the background potential which is nearly a constant for metals, and neglecting the electron electron interaction. So, very first thing I am going to do is relate the density of electrons to the highest state that is occupied. Let me explain. So, as I said earlier, if I look at this K space, every 2 pi by L there is one state. So, let us just make these states. These are all filled. However, each state can take only 2 electrons. So, this is 2 electrons, 2 electrons, 2 electrons, 2 electrons. In a metal bulk, there are huge number of electrons of the order of 10 raised to 22 per centimeter cubed. So, I need of the order of 10 raised to 22 states to fill per centimeter cubed. I need that many states to fill all these electrons. So, all these states are going to be filled. So, what I am going to have finally is go to a huge n value, and n varies only by 1. So, this is going to be roughly filled like this. The little up and down is coming because n changes by 1. Now, the scale is huge. I mean, I made this blue sphere to be of a radius only shown by this arrow, but consider this I am considering to be 1, the difference between 2 points to be 1, this is going to be huge, 10 raised to 23. So, this is a huge sphere. Now, why is it a sphere? Because the energy of all the electrons at the uppermost level must be the same for the ground state. Ground state by definition is the lowest energy state. If some electrons are at higher state energy and others are at lower, the electrons from higher state energy can come down to lower state energy and lower the energy of the system, finally until all the uppermost electrons have the same energy. So, what we are going to have is that in this K space, electrons are going to be occupied to a good approximation as a sphere up to a highest K, what I will call K Fermi. This is known as the Fermi wave vector. Kf is known as Fermi wave vector. So, the volume of this sphere, this is in K space, is going to be 4 pi by 3 Kf cubed. So, number of K points, and this is going to be the density of K points L cubed over 8 pi cubed times 4 pi by 3 times Kf cubed, because we have seen that per unit volume of K space, the density of K points is L cubed over 8 pi cubed, and each state carries 2 electrons. So, number of electrons is going to be 2 times L cubed over 8 pi cubed times 4 pi by 3 Kf cubed. And if I cancel a few terms, 2 and 4 pi goes, this becomes pi square, I get V over 3 pi square k f cubed. And this is, since I have box normalized over L, this is equal to the number of electrons in cube of size L, which is n. All right. So, we had taken these wave functions, we have counted the states corresponding to the wave functions which have been box normalized over L, and therefore, the number of k points came out to be whatever we have calculated, and that should be the number of electrons n in this. So, we have V times k f cubed over 3 pi square equals n, or k f equals 3 pi square n over V raised to 3 by 2. Let me show this pictorially. So, I have box normalized over this cube of size L, and then it keeps repeating and so on. So, according to normalization over this box, the number of states come out to be V times k f cubed over 3 pi square, including the 2 electrons per state, and this equals the number of electrons in this, and therefore, k f comes out to be 3 pi square n over V raised to 1/3, which is nothing but n over V is the density of electrons. So, this is going to be 3 pi square times the density rho raised to 1/3, where rho is n over V is equal to number of electrons per unit volume. So, we have related what is the highest occupied k vector, and the corresponding energy for k f is given as h cross square k f square over 2 m, which is known as the epsilon f or Fermi energy. Now, let us estimate the numbers. The density, as I said, rho is of the order of 10 raised to 22 per centimeter cubed, which comes out to be roughly 10 raised to 28 per meter cubed, and therefore, k f is going to be 3 pi square times 10 raised to 28 raised to 1/3. So, pi square is roughly 10. So, I can write this as 30 times 10 raised to 28 raised to 1/3, or 300 times 10 raised to 7. So, that is 10 raised to 9, and for 300 I am going to have about 6, 7. So, about let us say 6.5 meter inverse. K f is this meter inverse. So, we can say that in a metal k f is of the order of, let us say, 10 raised to 9 to 10 raised to 10 meter inverse, and epsilon f is going to be equal to h cross square k f square over 2 m electrons, which is equal to 10 raised to minus 68 times, let us say, 10 raised to 18 and 20. So, 10 raised to 19 over 2 times 9.1 times 10 raised to minus 31, which comes out to be 0.5 times 10 raised to minus 18 joules, which is equal to 0.5 times 10 raised to minus 18 over 1.6 times 10 raised to minus 19, roughly 3 electron volts. So, epsilon f in metals is of the order of 1 to 5 electron volts, given that density. Another quantity which is of interest is the average kinetic energy of electrons. So, energy of electrons is h cross square k square over 2 m, and so it varies from 0 electron volts to 5 electron volts or 6 electron volts, the highest the Fermi energy. And the way you calculate the average Fermi energy is, if I again look at that sphere, in a sphere of radius k, if I take a small shell of thickness delta k, the number of states in this is going to be, number of electrons in these states that are going to be occupied is going to be 4 pi k square delta k times 2 for the spin times v over 8 pi cubed, and energy of each electron is h cross square k square over 2 m. And if I integrate with delta k being dk from 0 to kf, this gives me total energy E of all these electrons. And through this I can calculate E by n, which will come out to be 3/5 of epsilon f, where along the way you will have to write n equals v times kf cubed over 3 pi square. So, this is the average energy of electrons in a metal. Then if you calculate the temperature Tf corresponding to the Fermi energy, it will come out to be Tf will be equal to Ef over k Boltzmann, and you will find that it comes out to be of the order of 50,000 Kelvin. So, what you can see is that if I write the energy on the y axis and fill the states that are filled are all the way up to a very high energy value. So, 1 or 5 electron volts is very high energy value, because this corresponds to roughly 50,000 Kelvin. So, what happens is, if I give energy of the order of room temperature, right, if I give the energy of the room temperature, the electrons that are going to be affected are going to be in a very thin shell around that energy. All other electrons are not going to be affected, because an electron out here, if it takes energy k T of the room temperature, it cannot go and move to the next level which is occupied. This electron cannot move up. So, all these cannot move up. Only electrons that can gain some energy is right atop within a thickness of k T. So, this thickness is going to be k T. So, if I calculate how many electrons are there within per energy range on the Fermi level, multiply by k T, that will give me the energy that they absorb. So, what I need is something called the density of states. At the Fermi level. So, that is what we are going to calculate next, the density of states. How do we calculate this? Again, I will go to the Fermi sphere, and if I take a thin shell of thickness delta k, then I have the corresponding delta E, the energy equals delta of h cross square over 2 m k square, which will come out to be h cross square over m k delta k. And the number of states, including the spin, between these two is going to be 4 pi k square delta k times v over 8 pi cubed times 2. This is the number of states including a spin between k and delta k, which I can write as delta n. This cancels for 2, 4 pi cancels at pi square, and this I can write as k square delta k v over pi square. So, if I were to calculate the density of states per unit energy range, delta E will be delta n over delta E, which will be k square delta k over pi square delta E times V. So, density of states per unit delta E per unit volume, which is usually written as epsilon, comes out to be, and I will leave it for you, proportional to some constant which depends on m and h and everything times the square root of epsilon. And density of states at Fermi level is going to be therefore that constant times square root of epsilon f. Going back to that Fermi level being filled, the electrons being filled, and very thin layer out here, those electrons getting excited. So, number of electrons excited is going to be density of states at the Fermi level times k T. This is going to be number of electrons absorbing energy k T. So, the energy itself will be epsilon f d epsilon f times k square T square, and you can see then d E by d T, temperature, which is specific heat, is going to be proportional to density of states at the Fermi level times T. So, the specific heat of electrons increases linearly with temperature, and it depends crucially on density of states at the Fermi level. Larger the density of states at the Fermi level, more the specific heat. That means, larger the Fermi energy, more the specific heat. So, this is just to tell you how the filling of electrons, how density of states comes into the picture. Any other transport phenomena or energy phenomena is again going to be confined to very thin layer near the Fermi level. So, with this I stop this brief introduction to metals and conclude this lecture by stating that number 1, free electron, or which is also known as free electron gas, provides a reasonably good first approximation to metals. Number 2, these electrons are filled up to states given by wave vector kf equals 3 pi square rho raised to 1/3, which is also known as the Fermi wave vector. Fermi energy is given as h cross square kf square over 2 m. Then the average energy of electrons is given as 3/5 epsilon f, and then specific heat of electrons is proportional to T and depends on density of states as epsilon f, the Fermi level and T, and density of states in 3D goes as square root of epsilon.